So it's time for us to learn the first law of thermodynamics. The first law is that we don't talk about the first law of thermodynamics. No, I'm just kidding. That was a Fight Club joke. The first law of thermodynamics is that the energy of the universe is always constant. Mathematically, it's written like this. The change of energy of the universe is always zero, which means that the energy at one moment should always be equal to the energy at another moment. But that doesn't hold for everything in the universe, or for depending on how we define our system. If we have something where we have a small system and an outside force is exerting energy onto, or exerting a force onto that, then we would have the energy initially plus the work that's being done on it is equal to the energy afterwards. Now, energy is still being conserved in the universe. That outside thing, something in the surroundings, is what's losing the energy in order for our system to gain it. But from an equation perspective, we do have a change in energy, and that's okay to have happen. It can also go the other direction. We can have energy that we start with, and then at the end, our object has been doing work on something else, which means it's actually the one who's losing energy. So we have energy 2 plus the work that it did on something else, and that would actually make it seem as if we've lost some energy. All of these are okay. But what this leads to is it leads to the formula that we're kind of going to keep in mind when we're talking about conservation of energy. We're going to basically say that the energy of a system is always going to be whatever energy it starts with, plus whatever work is done on it, is equal to the energies that it has at some other moment, plus the work that it does on something else. So this is the work that's being done on it, the work going into our system, and this is the work that's going out. We're going to be turning our energy bar charts into these equations where we say it's equal here at this moment as it is to that moment, with whatever work appearing also on our energy bar charts. So this idea is really central to AP Physics, and a lot of the FRQs and questions that you're going to be given are going to revolve around conservation of energy at some point. So much so that you want to write some version of this equation for basically every problem that you do on the AP exam. You have to make it specific to the problem, but if you can talk about the energies it has at the beginning and the energies it has at the end, you will get one of the points that you need. And actually, if you can write that much, you pretty much just have to follow some algebra steps to get all the way to the end. So get in the habit of writing these equations and knowing what you're doing. I'm going to give you guys a general algorithm to use to help us solve all of our energy problems. I can't give you specific steps on how to solve every problem, but I can give you some big general ones that we're going to use on all of our problems. So the first thing that we're going to do is we're going to sketch it. And once we've sketched it, we're going to identify our system. After we've identified our system, we're going to figure out our works and energy. Figure out what kind of work and energies are changing in our system. So if we're looking at it, we see things moving up and down. We know we have gravitational potential energy. We see things that are changing speed, or were moving and stopped, or stopped and begin moving, or we see spring, that would be kinetic energy. We see them suddenly rotating, that's rotational kinetic energy. We see something sliding and we know that there's friction. We know there's going to be thermal energy being generated. Look at the problem and figure out what kind of energies do I recognize are going to be happening here. Once you do that, then we can start drawing our energy bar charts. And that's going to give us our first measure, our first way of tracking. I know I have these energies at these moments, and I have these energies at these moments, and I need to remember as I go into my next step, and I write my conservation of energy equation. Right there, see, conservation of energy, that's our conservation of energy equation. We're going to write this, but we'll make it specific to our problem. So it might be something like, I have gravitational potential, then I don't have any work, but at the end, I have kinetic energy plus some work that was done. So make it specific to our problem based off of our energy bar chart. And then finally, our last step is just going to be to solve. We'll plug in the formulas from the formula dump. We'll manipulate the variables. We'll do some algebra. We'll work things out, and we'll figure out the problem. And it turns out these 5 steps are what every single conservation of energy problem is going to require. And we're going to do enough problems that you're going to see that really every single energy problem is exactly the same as far as following these steps. And you should get very good at not just the energy, this is also going to be a great chance for you to get better at some of the algebra skills so that when we do our review of the forces and kinematic stuff that you struggled with early on, you'll find that you'll actually be more prepared for that because of all of the algebra steps we're doing in this unit. So that's everything that we need to know about conservation of energy. Thanks.